I'm Charles Antonelli, and for those of you who came in late, a little bit later, these slides are available at that link. If you look for the Introduction to Supercomputing Workshop under my smiling face on that URL, you'll get a copy of the slides I'm going to be lecturing from. It'll be useful because you'll be able to, if you have your own copy, you'll be able to copy text from there into your command windows on occasion. So this is an introduction to supercomputing workshop, and as Andy mentioned, my colleagues Leslie and John are here. They will be acting as proctors, which means that if anybody gets stuck for any reason, none of this stuff is hard. It's not difficult. What you all are doing is difficult. This is just arcane. And it's easy to get off the path, and there's no reason to suffer. Just ask John or Leslie to come, and they'll be more than happy to help you. If one of you is Dylan, we need you to request your login on Great Lakes so that we can provision it so you can get on and actually log into the cluster.
I don't see him here. He mentioned he might not.
He might not be here. Okay. All right then. Then we'll move on. So today we are going to cover these topics. Much of this will be very fast. We only have an hour and a half. And so I'll talk a little bit about the architecture of a computing cluster, Great Lakes, a very brief amount on the command line and how to use it. We'll talk about the mechanics of using Great Lakes, how you log in, what network you have to be on, that sort of thing. And then we're going to cover two ways of using high-performance computing cluster. The traditional way, which is usually used for what we call production runs, if you have a lot of repetitive computing to do. That'll be a batch method. You write scripts and you submit them to the cluster scheduler, and it will schedule the work for you in a very automated fashion. And we'll see an example of that. And then there's also an interactive mode of using the cluster where you can have a desktop that is open on a compute node, and you can compute in interactive fashion. And we have an example that uses GPUs to do some, well, by now, elementary large model machine language processing. And then at the end, there are some slides about support. So Great Lakes is the name of our computing cluster. It's owned and operated by U of M's Advanced Research Computing Organization. All of us are part of LSA Technology Services, and so we work with this group in order to provide services. So we are here for you, not just now, but later when you are using the cluster for your computations. If you run into issues or problems, your requests for help will be routed to one of us. And we also have two other people on the team that are not here. So here's a cartoon of what the cluster looks like. How many folks have done cluster computing before? Okay, so this will be review for you. I apologize. There are a number of compute nodes, mostly the same. Those are the green boxes. You don't log into them. In fact, they're walled off from that. But folks log in to the cluster by logging into a login node. The blue boxes, and that's where you prepare your work, copy data, create the scripts, submit the jobs. And then there's a scheduler that takes the work that you want the cluster to do and farms it out to, according to the resources which you've asked for, to one or more of those green boxes to when compute or when compute resources become available. There's also a data transfer node that is useful for copying data on and off the cluster, including very large amounts of data. It's probably not necessary for what you all are doing in the class, but it's there. And then there's a number of different storage systems that the cluster is connected to. A standard node is really just a compute your system with 36 cores, 180 gigabytes of available RAM, a small amount of local disk, and it's connected by a very fast network. These are all resources, cores, RAM, and then compute time that you'll be asking for when you are scheduling jobs. Some nodes have additional capacity. So there are some nodes which have much larger amounts of memory for those tasks that need it. And we'll be using another kind of node that has GPUs that are attached to them for performing GPU computations. Very brief introduction to the command line. So Andy has already told you about this. Yes, he has a very good subset on his Andrew's BrainBook site called Unix for Neuroimagers. If you haven't gone there yet, that's a great place to go. And although it says Unix for Neuroimagers, everything that he says there applies to Linux as well. Although under the covers, Linux is quite different. The Linux kernel is quite different from the Unix kernel, but the user API is exactly the same. And so I would direct you there. There's also a book, an ebook called A Complete Introduction to the Command Line. That's also very good. And it's a Creative Commons licensed version, so you can get that for free by downloading a PDF. And there's some advanced topics entitled Adventures with the Linux Command Line for further reading. All I'm going to do here is just briefly give you enough so that we can get on and do things, and then I'll cover the rest of what we need while we're using it. So typing at the shell prompt is, if you've not done this before, you basically type commands into a command processor called a shell, and it accepts whatever you type, executes that command, and then goes back and asks you for another command. So it's different from a GUI in that you have to know the commands you want to use and what all the arguments to them are in order to accomplish what you need to accomplish. These are just commands that will let you edit while you're typing. In the simple case, you just type and hit enter, but you can move the cursor with the arrow keys if you need to make corrections. If you want to start over, you can type Control-U, and that will erase everything. The thing to remember is Control-C. In almost all cases, if you're stuck or you get frustrated or you want to start over, or the command that you've started doesn't seem to be finishing, or it's doing the wrong thing, Control-C is an interrupt that will stop the command if you are running a command. If you're still in the middle of typing a command, you'll get a new line and you can start over. It's an easy thing to do. The other thing is that by using the up and down arrow, you can move back through the history of the commands you've previously typed. The shell remembers what you've typed line by line. And you can go back to a previous command, hit enter. It's a lot faster than typing it all in again. And at any point you can edit. When you want to get out of an interactive shell session, type exit, and you will and the shell window will close. In a pinch, if things get really wedged, every so often Control-C doesn't work. And in that case, simply closing the command window from the GUI will kill the shell, and you'll be back to normal. That's all I'm going to cover here. And as I said, we'll answer questions. So the mechanics of getting onto Great Lakes, you need three things in order to be productive on the cluster. You need a user login, you need a Slurm account, and you need Duo. So the user login you request, you've all asked for them, and you all have them. And that login is just a regular login on a Linux box. And so you connect to it with your unique name and your Kerberos password and Duo. And then that will get you onto one of the blue boxes for logging into the cluster. If you actually want to submit jobs, they have to be submitted against an account. So the cluster charges for jobs, and those charges are posted to the account. We're going to be using the account named training for this work. You all are in this training account. It's got limited resources, 4 cores, 20 gigabytes of memory, and you can run for an hour. So it's not a whole lot. But you can substitute any account that you have access to for the account name, and your job will run against that account. Some accounts have much larger limits. In exchange for that, the training account has higher priority. So if the cluster is busy, your training account jobs will start faster. And you'll be in this account for 3 days. So if you want to experiment afterwards, you can still use it for that time. To connect to Great Lakes, you either have to be on campus, plugged into a wired connection, or on M-Wireless, and you can connect it directly. Otherwise, you have to use a VPN. All the links in this presentation are live, and the presentations stay on my webpage, so if you want to come back for reference. This points to a page. If you have, for some reason, not gotten away with not yet installing VPN on your laptop, it's probably a good idea to do so you can get at Great Lakes from off campus. By the way, if there's questions or anything, sing out. We've got a small group here, and there's no reason to be shy. So to connect to Great Lakes, there's 2 ways to do it. The command line way, and then the interactive way. So for interactive, on all operating systems, find and open a terminal window. And in that terminal window, type SSH, your unique name, at greatlakes.arc-ts.umich.edu. You'll then get connected to Great Lakes, use your Kerberos password to authenticate, and then Duo for 2-factor, and you will get a remote command shell. So let's do this now, if we haven't already. I've already done it, but is this window too small for people to see? Let me do this. Okay, so SSH, my unique name, at Great Lakes, arc-ts.umich.edu. There are times when you can omit the unique name, but in many cases you can't, so I always use it. And you'll get something like this, and then it'll launch your password. If you don't see this screen, if all you see is nothing, that means that you're being blocked from contacting the cluster. That means you have to get on VPN. So my Kerberos password. Again. And then Kerberos. I have some extra options, but you probably only have a couple. And then authenticate. You won't see this, and hopefully, you won't see this, but if you do, that means that your home directory space is getting full. And what you should see is a prompt at the bottom. This is the shell prompt. It will give you your unique name by default, and then whichever login node you've logged in on. In this case, I'm on GL login 3. And so at this point, you can type commands. So for example, if you type date, that will get to the top. So this is a general purpose command that just tells you the time and day. It'll do a bunch of other stuff too. You can give it arguments like date minus U, and it'll give you the date in UTC. If you are the super user, that is, if you have administrative authority, you can use the date command to change the system's date and things like that. I'm going to show you a useful command. If you're ever confused about a command and what it does and how to use it, there is a command called man, M-A-N, short for manual. And you can type that and the name of the command, and you'll get a nice sort of a ASCII listing of the user manual for for that command, which tells what the name is, what it does, and then how to use it, and then a list of arguments. So here you can see the -u is in here somewhere. You can page forward in this listing by hitting the space bar. You can page backwards by hitting the B key. And you can, if you want to look for a particular string, you can type a / and it'll appear down here. And then whatever string you're looking for, like -u, and it'll scan forward and find the first occurrence of that string. If you type N, it'll find the next one. It's an easy way to search through a long man page. And when you're all done with it, you can type Q to get out. This is a paradigm. There are other commands in Linux that have exactly the same way of controlling pagination. And this is one of them. I'm going to show you a command, top. If you type top, hit enter. This is an example of a command that doesn't stop. So all the previous ones, they did something and exited. This one is a tool that shows you the top processes on the system that are using CPU resources. So this is a login node. The load average up there is 10.6. That means there's 10.6 processes running right now. And these are what they are. Each one of them shows you who the owner is and how much memory it's using and what percentage of a CPU it's using, how much time it's accumulated up till now. It's kind of a way to see how busy the node is and what other people are doing. But it won't end. So in order to get out of this command, you can type Q for exit or a Control-C. I'll use a Control-C, and that's what gets you back to the command prompt. All right, that is the end of the quick introduction to command line. Any questions anyone has? Sir?
So the top command essentially shows you all the CPU, GPU processes running across the board for every user?
No, all the top command does is it shows you who is running CPU processes on the node that you're logged into. So there are commands which will show you what everybody is doing on all the nodes on all the clusters, which I can show you later. And there is another very useful command that we'll get to called nvtop that you can download too and use. But I have a copy for you that shows you what the GPU utilization is for whatever node you're logged in on. We'll see that later. That's a good question. Visibility is sometimes not what you think it is. Let me just do this. This is the command that shows you what's going on all the cluster, on all the nodes of the cluster. So let me do a clear. If you type state and then a vertical bar and then less. It's a good time to talk about this. So in Linux command line, you can create pipelines that are indicated by a vertical bar. What this means is the state command runs and does something, produces some output. That output is then fed into the input of the next command, which in this case is less. Less is a paginator that shows you text a page at a time. We just saw it in the man page. But here we're using it explicitly. And so this shows you the first page of the overall system information. This shows you for every compute node, they're all named GL 4-digit number, how busy it is, how many processes are running on it, what percentage of the memory is used, all of that. If you hit the space bar, you'll see all of it. A little bit hard to read, but you can widen your screen and you'll be able to see it all on one line. Just to give you an idea, if you hit the up arrow and backspace and put in WC space -L. So WC is a command. It stands for word count. If you give it the -L option, WC will tell you how many lines of text you gave it. That's all. So if we run state, which gives you a big listing, and pipe it into WC, it'll tell you how many nodes there are on the system, because there's one output line for each node, right? And so there's 544. There's a header line in there too. So this is sort of the Unix philosophy, which Linux has picked up, which is you create a bunch of commands that kind of do simple things, and then you string them together with pipelines, and you can get a lot more efficiently through your work. All right, let's go on. So the next thing to do is Andy has made available a set of data that we're going to be running today. And what you will want to do at this point is to type this command into your command windows. You can either type it in live, don't do that, or copy it from this screen and paste it in your command windows. So I'm going to demonstrate this, but I'm going to move my flanker to, because I've already done some work here, into a different place. All right, so now if I come over here and just scan all these, copy the text, and then paste them in over here. So this line here, CP minus RP, this copies this entire directory, NFS Turbo, LSA John, Workshop, Supercomputing, Flanker, to tilde. Tilde is shorthand for your home directory. And then after that, it changes to that directory. And I'm in that directory now. The pwd command is another useful command that will show you the current directory that you are in. And so you can see that my current directory, where I'm currently working, is now Flanker. When you log into a system like Great Lakes, you will wake up in your so-called home directory, which for me is home / my unique name. And Flanker is a directory in that home directory. And if you type in ls, you should see something like this. In particular, there are 6 subdirectories, sub-01 to sub-06. We'll be using some of those today. The ls command shows you a short listing of the current directory. Just gives you a list of all the names. If you want to see some details, type ls minus L for long listing, and it'll give you the same list, but it will also tell you things like who owns the file. In this case, this is me. When you do yours, your unique name will be here. The size of the file, when the file was last changed, and then information about whether it's a file or a directory. If it has a D at the very beginning, it's a directory. Sub-01, as you can see, is a directory. All the subs are directories. Dash means file. And then something about the permissions, which we won't really get into, but basically this tells you that you have access, complete access to the file, read, write, and execute. And everybody else, other people, people in the group of the file, which is LSA John Turbo, for this data set, also have universal access. But people who are neither you nor members of this group have only read, execute, so they can't make changes. They can't delete files, they can't edit files and make changes. This is a common way of sharing files. You can also say ls sub-01, and it will give you a listing of what's in sub-01. So we'll get back to this, but if anyone has an issue with these copies, let us know, because we're going to be using this from now on. Very briefly, Great Lakes has a lot of software on it, including the FSL software that you're going to be using. It's initially not available by default. You have to ask for it. And so there is a module command where you can say, I'd like to use the FSL software, and it will load the software into your environment so that you can use it. We have several hundred titles, and you can load modules for any of them. There's a list of software there. Modules the modules command is a way to make software available without it being painful for you. There are a whole lot of changes which have to happen to your computing environment so you can access certain software. You don't have to worry about that if you have a module command. And so module load and the name of the module will make the software available. So module load FSL will make the FSL software and all the functions it has available to your session, either your interactive session, like you can enter this command in your command windows, or when you're submitting batch jobs, you can add that to your batch job and it will make things available there. This is mostly for review, these next two slides. I'm not going to burden you with a lot of this, but I just want to point out that there are a number of different storage systems you can use on Great Lakes. Everybody wakes up in their home directory, which is a standard directory with 80 gigabytes of quota. For truly large computation, there is another directory available called Scratch, where you can write lots of data very quickly. It is intended to be used while you're computing, and so files get purged out of there after 60 days. It's kind of a standard thing. There's also a local disk attached to every compute node, which we're going to be using for the second example because it's very much faster for large numbers of small files, but it's harder to use. And then there's turbo storage, locker storage, and data den, which are different types of storage with different storage characteristics and costs and access times that you fit to your workflow. And there's a storage finder that's actually quite nice. You sort of tell it what you want to do with your data, and it will say, well, here's the storage you might want to consider for that. These are all charged for things, and many departments subsidize those as well. And you may already be using them.
For the Scratch directory, how does that 60-day clock reset? Do you just have to read a file? Do you have to write a file?
You just have to access a file. So if you are actively using the data, so you're reading it, say, that's good enough. You don't have to be making changes to it. Enterprising individuals have written scripts to touch their data so that they're not using. Like the cluster operators will send you hate mail if you do that. But in general, the idea is that this is data you can use as much of that 10 terabytes quota as you need in order to get your work done. It's just not a place for long-term storage of data. That's what these are for. Copying data. There are two ways to copy data onto and off the cluster. So data files, programs, things like that. The SCP command works just fine. This is a standard secure copy tool that you use to copy files from one place to another that you probably already have used. You can use it with Great Lakes as well. Just use the node name Great Lakes-xfer, and you'll be using that black node for doing the copies. The advantage is if you use the transfer node, you don't have to do the dual authentication thing for every copy you do. If you use some other node like Great Lakes, you'll have to. If you're used to using any of the standard GUI applications to copy files back and forth, they will work just fine too. One sticky point is if you create files on a Windows system, text files, I'm talking about only text files now, and you copy it to Great Lakes with any one of these mechanisms, the line endings in those text files will be wrong for Linux. Windows ends lines or separates lines with a carriage return line feed character, 2 characters. Linux only uses a line feed. Most of the time that doesn't matter. The files look the same if you list them, but some software does not like to see that carriage return. So there's a program called DOS to Unix. You just point it at the files which you've copied over, text files, and it will make the changes. It's in place. It's quite safe to use because it reads every byte of your file before it makes any changes, and makes sure that every character in the file is a plain text character. And if there's even one character that isn't, it won't do anything, because it might be binary, and you really don't want to make those changes in that case. The safest approach would be to edit your files, create your files on Great Lakes, on a Linux system in the first place. But
let's say you're copying a pretty large data set, and there's some kind of interruption at some point. Computer goes to sleep or something like that. Is there a way to resume everything or to continue your SFTP without overwriting everything that's already up there?
what a great question. Yes, so there is another way to copy data, which I'm not going through here, but the answer is yes. With these tools, the answer is no. So if you do an SCP command, you have to stay connected for the entire hour or however long it takes to copy your ½ terabyte, right? If at any point in time you lose the connection, that's it. You have to start over and overwrite the data. Again, there are tools like rsync, if you're familiar with that, that will actually do what you say. They will pick up where you left off, but you still have to be connected while it's running. For larger copies, we recommend that you use a tool called Globus, which is a data copying service where you basically, it's web-based. You connect to it. The interface is very much like these, if you've used these before. You tell it, I want to move these files from here to here, and it'll do it in the background in the cloud while you, local cloud, while you go off and do other things. So you don't have to stay connected, whatever. When the copy's done, you'll get email. And so that's a good tool for larger copies. If there's time, we'll go over that a little bit. I can show you what the interface looks like. All right, batch operations. So we're trying to do batch jobs. When you are using a computing cluster, you're typically implementing some type of workflow, right? So if you're doing a workflow, you will have more than likely a script that you've written that implements your workflow, right? Several steps, you're copying files, you're running separate programs. In fact, there are scripts that Andrew wrote that will do the running of the FSL tools. Normally, you would just run those at the command line, and they'll run. When you're using a computing cluster, you take that workflow script, you add some information to the top of it that says how many resources I need in order to do this. How many cores do I need? How many copies of the software? How long is it going to run? How much memory am I going to need? And that turns that script, that workflow script, into a batch script. You then give that script to the scheduler via a command. The scheduler takes that, puts it in the queues. When resources are available to run your job, it will copy that script to whatever green box is going to be running on, or boxes, and then lets it go. And it takes care of wiring up all the connections so that everything gets copied in the right places. The compute nodes have access to the same file systems that the login nodes do, so it just runs as though you were running it yourself. Because you're not running it yourself, you don't get to see any of the output that the script itself is producing, right? So that output is captured by the batch system and put into a file. We'll see that, and that file is updated in near real time, so you can watch the progress of your script. You can arrange to have email sent when your job begins, when it finishes. The advantage to having it sent when your job finishes is it will tell you how many resources it actually used. How much memory, how much CPU time, which you can then use to make a better estimate for the next time you run your job. And if you don't like what your job is doing, you can check its status, and you can delete the job. It's the exact equivalent of typing a Control-C on an interactive command. You run a command that will send a Control-C to your running job, and it'll kill it. So this is what a batch script looks like. They're all bash scripts. Down here is what I call the payload. So this is what the workflow actually is. So this is a very simple example. We're unloading any previously loaded modules. So we start with a clean slate. We load the R interpreter, and then we run R in batch mode, and we give it an input script to process and an output file name to put the results. This is what you would run at the command line where you're running this interactively. All of this are the commands, the options to the scheduler that tell you things like the name of their job, when you want to get mail, how much memory your job wants to use, how much time your job uses, what account to use, and what partition. Partition is what type of node. And so the standard partition are those 180 gigabyte 36 core nodes I was talking about. When we do the GPU work, we'll actually be using a GPU partition. These three here sort of describe the geometry of your job. What we're asking for here is one node, one task. A task is just a Linux process. So a standard serial piece of code would be running inside one Linux process. And then how many CPUs you want to give to each process. Some processes, some code is multi-threaded. You can give it more cores, and it will run faster. And here's where you say how many CPUs you actually want to use. Some of these are hard and fast limits. If your job runs and it goes over your memory limit, it'll get killed. If your job runs over the amount of time that you said it would take, it'll get killed. This is because the scheduler creates a schedule of all the jobs in the system, which looks like a giant Tetris pile. And if you all of a sudden start asking for more than what the schedule has given you, it messes everybody else up. If you try and start more threads than you have cores, your job's not killed, but say you have 8 threads and only 4 cores. Each of those threads will only get half a core, and your code will run half as fast. All right, so once you have one of these, sir.
I can actually ask a question about the previous one. A lot of times I have personally at least run into a decision where I'm not really sure how much memory my script will require to run.
Yep.
And sometimes it will get killed because it runs out of memory. Or is there by any chance a way where we can predict how much memory the script will require? Or is it just purely trial and error?
So this is a very good question. We don't have an oracle, so we don't know, right? So typically, if you've run this code somewhere else, for example, on your laptop or lab machine, the run times will be about the same. What the cluster gives you is nodes that are about as fast with CPUs that are about as fast as yours, but it gives you tens of thousands of them, so you can run in parallel. But a good number to start with is, well, how long does it take on your machine? If you don't have that, then pick a large number. So no job can run on the cluster for more than 2 weeks. So you could give, for example, 1 day or 2 days, a very large amount. This will, in some cases, make your job not schedule as fast, because the scheduler is going to say, okay, I'm going to reserve like a day for you. But with the current cluster configuration and usage, it's not a problem. So you run for a day with a day estimate. You look at the job end email, it says, well, it took 15 minutes. Well, you maybe add a little bit to that and then use that for your next estimate. So it's kind of a trial and error process. For workflows that are highly data dependent, some minimization processes are highly dependent on the particular data, and so your runtimes can vary a lot based on the data. In that case, you just have to add more time to it. There is no better way, unfortunately. All right, so to submit a job, once you have your batch script, you give it to the sbatch command. A successful job submit will return an 8-digit number. That's your job number by which the job is known while it's in the system. You can then use that job number to say what its status is, SQ minus J, job ID. You can ask for all the jobs you currently have by using the -u option, or you can use this handy command that we wrote, SQ, that does all that for you and shows you all your jobs. You can also ask about anybody else's jobs too by typing their unique name. And then to delete a job, you type scancel and the job ID. So we're going to do a single run of the flanker code. So, and then after that, I'm going to generalize that and show you how you can run multiple executions of the same flanker code in the same job across a number of different data sets. But first we're going to do it by hand. So let's cd into flanker. I am going to so you should cd into move flanker to, don't you type this is me, flanker.new, and move flanker.save into flanker. So I'm just going to the copy that I have. And in here, there is a directory, there is a file called analyze sub01.sh. So let's take a look at that. In order to edit files on the cluster, you can use whatever text editor you are most familiar with and happy with. The cluster supports VI, Vim, Emacs. If you don't have a favorite editor, a good editor to use is called Nano. So Nano, and then the name of the file. Enter. Nano is a good editor to use because it's a powerful editor. It has a lot of options, but it also has a particularly simple mode for editing files by moving the cursor around. So this will show you the first page. You can move the cursor around with the arrow keys. If you go down, it will move down. Anything you type will go in where the cursor is. You can also delete characters, and so that's an easy way to edit the file. We're not going to edit this, but I just wanted to show it to you. So this is taken from an existing script. This assumes that the brain data is in a directory named sub-01, and so it will change into that directory, and then it'll run through a set of options. All of these commands are commands that are part of the FSL archipelago, and so this is your workflow. And at the very end, it will end up running these commands. It will create two directories and put the results there, and then it's all done. In order to exit out of this, type Control-X, and you'll be back on the command line. If you've made any changes, it'll say, you've made changes to the file, do you want to save them? And then you say yes, and then you save them. Now let's take a look at the batch command that we're going to use to submit flanker batch underscore sbat. So this is the actual batch job we're going to be using. This will give a name, a maximum runtime of 1 hour. This will take about 10 minutes to run. So this is a nice safe number. 1 node, 1 task per node, 1 CPU per task, 8 gigabytes of memory. The account I'm using is training. You can, if you want to, change this to any account that you have access to. Oh, by the way, let me go on here. So we're saying we don't really want any mail, but I'm going to change mine. I could at this point change it to say all, and then I would get all my job emails. Here's where I load the FSL module. This just outputs some information for debugging later if it's necessary. And then the actual payload of this command is where we're running that script we just looked at and that will generate the workflow. Control X to get out. So now run your job. You would say sbatch, and then here's a little shortcut. If you type exclamation mark $sign to the shell, that is shorthand for the last word of the last command. So in this case, that will use flanker bash at sbatch, so I don't have to type it again. Now it's submitted the job, and here's a job number. If I type SQ, it will show my job here. You can tell by the name, flanker. I got some other stuff running, that's what this is. R means that the job is running. If it says PD, that means pending, that means it's waiting to run. And eventually it will start. When a job is running, it will show you how long it's been running for, something about the resources it's using. It's using one node and one core, and it will show you, one node, one core, and 8 gigs of memory. And it will also show you the name of the node that it's running on. You can, remember I said that the compute nodes are inaccessible to you, right? I lied to you. You can actually get on them. You can get on a compute node while you have a job running on it. And once that job exits, it will kick you off. Why might that be useful? Because we can use that top command. So I'm going to SSH to that node. Now I'm on the compute node because my prompt has changed from GLlogin3 to GL3026. I can use that top command now. I can say top -u and then my unique name. The -u option to top will show you that same listing of jobs, but only your own. And so you can see that up here, this is my job running. It's running MC Flirt right now. You'll see that a large number of different commands as the workflow runs through. And it's using one CPU pretty much 100% of the time. Control C to get out. If you just run top, there's a whole bunch of other stuff happening on this node, you see. It's just that it doesn't have anything to do with us, and the scheduler has guaranteed us on that compute node the resources that we asked for. So this will run for a while. How many folks have actually started this? Okay, so yours will run for maybe 10 minutes. I've already run it. So if you go into sub-01, what it will do is it will create directories run1.feat and run2.feat. This here, every time you rerun the workflow on the same brain data, it will create a new run1.feat with one or more plus signs. So this one here is being created by the job I just started. These two were run earlier this morning. Sir?
Just so I could say a few words. This data set's a very simple flanker task. That's my data set. Computing contrast between incongruent and congruent, and then providing the output for each subject. I also just a question. So just to clarify, your job gets submitted kind of randomly to one of these compute nodes. In this example, GL3026, you went to that node, and then you can look in real time what command is happening.
Yes.
Right now. Okay.
That's what it's used for. So it gives me a warm feeling to know that my stuff's actually running and using the resources that it's actually asking for. There's another command you can run where it will tell you how many of the resources it's used. I can show that to you because there's a command called SACCT, stands for S account. If you type in that command, it will show you all the jobs you ran today. You can ask it for more stuff, but it'll show you by default everything today and what its status is. So you see that I ran flanker up here sometime in the past. I ran multi-test a bunch, but there should be a regular flanker job here somewhere. Yeah, like this one here. So this job number right here, this is a completed job. It ran this morning at 10:41. I can type the following command: my_job_statistics, and give that job number. Well, anybody remember what that job number was? How about this one right here? Yeah, thank you. So I can type my job statistics and that job number. And what it will do is it will tell you how much use you made of the resources that you asked for. So we asked for an hour. The job ran for 7 minutes. We used, during that time it was running, we used a CPU, we used overall that CPU 82% of the time. That's good, it's not great. What you'd like to see here is a number above 90. Typically these numbers drop because of I/O. And this workflow does a lot of I/O, and that's why this is not as high. If you are running with multiple cores, remember I said about a warm feeling? If you're running with multiple cores, like 4 cores, and you run this and you see that it's only keeping 1 core busy, then there's something wrong with the command you invoked or how you invoked it. And you can then go back and figure out. Some commands you need to tell how many cores to use. Other commands pick it up automatically. And if you run into a command that needs to be told how many and you didn't, it's going to use 1, and you're going to be wasting a bunch of resources. So that's what this command is useful for, too.
So another question.
Sure.
When you start charging people for the resources they're using, is it like prepaid gas? Like if I say, I think I'm going to need $20 of this, I only use $10. Do I get that?
Okay, that's a good question. So you are charged for the resources that you ask for the actual time that you are using them.
Okay.
So it's worse than that. So if you if you ask for 4 cores and you only use 1, you pay for 4. If you ask for 10 gigabytes and you only use 1, you pay for 10. If you ask for, because those resources are allocated to your job, no one else can use them, so you're charged for them. But if you say I want to run for 2 hours and you run for 10 minutes, you're only charged for 10 minutes because the resources are given up at the end of the 10-minute period. So that's why it's important to match the resources that you ask for the ones you actually use. That's what part of the reason for this command. There's another command you can run called my_job_estimate. This one is and all these commands that start out my under will give you a, if you type -h, will give you a, like usage list. If you tell it the resources you want, it will tell you how much it will cost. So you can say my job estimate. Suppose I want to use 4 cores, so -C4. I want to use them for 10 hours. -T 10 0 0 0 0. And I want to use 8 gigabytes of memory. So 4 cores for 10 hours is 60 cents. Put another way, like you can use a single CPU core for a month straight, and it's $10.82. So the cost is quite economical unless you're using lots of cores, lots of memory for lots of time. But this is a good way of estimating what the costs might be.
That's extremely helpful. I had a question concerning the previous command. So for instance, I was looking at some of the previous jobs that I run on the cluster, and for some reason I invoked 6 cores for 1 node, but my CPU efficiency is around 27%. Would you say that this is probably a sign that I should be using a lower number of cores?
Probably, yes. Unless your job is doing just a whole lot of output. That indicates that there's some idle cores there. And that's, so when you run that code again, you could SSH onto the compute node and use top to see what that percentage is. And if you see you know, like 100%, even though you've allocated 4 cores, you see 100%, you know you're only using 1. If you see like, you know, 350%, that's TOP's way of saying you're using 3.5 cores fully. Yep. And we can look at that after class if there's time too. All right, so so that's how you run a singleton, right? That is, the directories run on, I think my job is done now because I have like 2 of these, but ls run1.feed. This was all created by the workflow. But it turns out that we have 6 of these, right? So, and I understand that there's a whole lot more that we could have here, right? So, yes, you could run a separate job for each one of these, and people do that. But that means you have to go into each of the jobs, change the script so that it's now changing into sub-02 instead of sub-01, and then you have to modify the batch script to run the right. And that's an error-prone process. Some folks write scripts to generate batch scripts to then submit them. That works better, but it's still kind of, it's a lot of work. And so this is such a common thing. You know, parameter sweeps have the same issue. You're running the same application code over multiple points in some n-dimensional space. And you might be running hundreds of thousands of these. You don't want to be creating separate batch jobs for each of these. This is such a common thing that the clusters, all cluster batch systems support what's called a job array. So you have one batch script that you submit, but you tell the scheduler how many elements there are to be in this job array, and it will like look as though you have submitted all of those jobs. And it tells each of those instances of the job array, knows what its ID number is, and the name of the game is each one has a different ID number. That number is then mapped to the data that that particular job array element needs to use, and then you just step back and run one, right? So that's what we're going to do next. First, I want to show you, so we could do this, we're not going to do this. This would just show you how painful it is, because you have to edit the files and copy them around and all of that. I showed you some of these commands already. My accounts will show you all the users, my job estimate, my job statistics. My usage will show you how much you've spent this month. My account billing will do the same thing, and my account resources will just show you how many resources are available in that account right now if you wanted to start your job. So it's a way to see if resources are there before you start your job. If resources are not available inside your account when you submit the job, it will wait until they become available. So job arrays, you basically add the -- array option, and you say how many job array elements do I want to create. And if, for example, and these are integer numbers, so m-n, like 1-10 means create 10 copies. Each of those copies will have a separate number in its environment, so it knows what copy it is. There's a special environment variable called Slurm array task ID that will be set to each of those index values for each one of the job array elements, and then you write your job to use that number to get at your data. So let's take a look at analyze_sub.sh. I made a copy of that in your directories. So here you should see an analyze sub.sh here, the one without the number. So let's look at this. This is exactly the same script as before. The only thing different is instead of saying subject equals sub-01, it says $1 here. That's a parameterization. In a bash script, this means use the value of the first argument that I was given when I was run. So now you're going to see how we're going to parameterize this. Let me do a Control-X to get out. If you want to see what's going on, you can say diff that with analyze sub o1.sh, and it will show you the differences between those two text files. So diff's a very useful command for showing differences in files. Literally the only difference is what I said. Everything else is the same. It's a useful command. Now if we take a look at the actual batch job, we're going to look at multibatch.spat. This is almost exactly the same, but not. So all of this is the same in the batch script, but up here we've added dash dash array equals 2-4. This means we are going to start. There are going to be 3 array job elements. They're going to be number 2, 3, and 4. It will be as though you submitted 3 separate jobs, and each of those is going to use these resources. So each one of these job array elements gets these resources. And at the very end, we've changed things a little bit. Okay, now we're still invoking analyze sub.sh, but now we're giving it a parameter, which is going to be the subject number, right? So what we need to do is we need to map Slurm array task ID 1 to sub-01, 2 to sub-02, right? And that's what this step does right here. This simply takes the Slurm array task ID, and this printf .02d will display that number as a 2-digit leading 0 number, right? So it turns 1 into 01 and 2 into 02, etc. And then that gets added to the end of the string sub-dash. So now you get sub-01, sub-02. That goes into this variable, which is then used here. So this replaces all of the having to copy files and make multiple copies. And if you decide tomorrow that you want to run 1-100, this script will just scale and run 100. So it's an important tool. So let's run this. I've already run this too, but I'm going to run it again. Because I want to, so sbatch, multibatch. That's a little more complicated. So you see, if you go by the names, there are 3 multi-test jobs here. These 2 are running. And so we are creating, and it may well be running 02 and 03. This one up here is pending. So it's not running. And why is it pending? Well, it will tell you. When a job is running, it puts as the last item the node it's running on. If it's not running, it will tell you why in this cryptic QoS max memory per user. So remember I said the training account has limits on it? One of the limits it has is you can't have more than 20 gigabytes in use for any user at any one time. How many gigabytes does each of these jobs use? 8. So you can run 2 of them at once. The third one's got to wait because it's going to use more memory than the 20 altogether, right? And so this job will wait. You'll see the same thing in yours. This job will wait until one of these is done, and then this one will start up. And that's all there is to it. If you look at sub-02, for example, you'll see I ran this earlier this morning. There's a run 1 already in there and a run 2, but it's now creating run 1 plus.
So let's say my goal was to get all 3 of these jobs done as quickly as possible, would it be more efficient instead of a job array to submit each of them as separate jobs?
No, because the limit is a function of the account you're running it under, not what you're doing with. So if you want to get these, and this is a good point. If you want to have 10 of these running at once, you need an account that will let you do that. Most accounts don't have limits on things like number of cores and amount of memory, but shared accounts do. So like training, departmental shared accounts in general, and some PI accounts will have those. But in general, if you get, for example, if you have an RCP account, so AJON 0, has no limits on it at all, except I think there's a $100 a month default spending limit on it. So if you were to run this under age on 0, you'd see these all running. You'd see 10 of them running. You'd see as many free cores as there are on the system in the current partition will run at the same time, which is important. If each one of these takes 10 minutes, and you want to run 100 of them, I'm getting excited, right? So each of those takes 10 minutes. If you got 100 cores, you get 100 results in 10 minutes. That's the power of the cluster. Okay, so I would love to talk more about this, but I got to move on to the next example, which is a little bit more automated. But I want to introduce. First off, any more questions about this? Okay, Great Lakes interactor operations. This is the other way to use the cluster. If you have applications that are graphical in nature, so like you need to operate a GUI or primarily, being able, like SSH, into a cluster is not a great way to use it. Some commands will let you run them in batch mode, but it's kind of clunky. So there's a way to connect to the cluster graphically and provide a graphical desktop, and that's called Open on Demand. This was developed at OSU, and we made some changes to it. Essentially, you go to a web page, you tell the web page how many resources you want, just like we did in the options of the batch jobs we already ran. And then we start up an interactive desktop. That desktop then has all the resources that we asked for, and it gives you a desktop you can use to like run commands and start things. And we're going to use that in this example. I just want to point out that there's a rich set of things. If you're into Jupyter Spark, there's a desktop for that. Also, recently added is a Visual Studio Code desktop. So there's a number of different features, different applications that you can start up right out of the box. Or you could ask for a general purpose desktop, which will give you a desktop and let you do all that stuff, by hand, which is what we're going to do. So what we're going to have to do in order I have an example that was suggested by Mark Champ, who's another member of our team. This is an AI image generator. It's kind of a turnkey AI image generator, but it requires a graphical desktop session to drive it. So we're going to start a 1 GPU open on demand session because this code's going to use a GPU. Once we have that desktop, we're going to open a terminal on that desktop and change directory to this subdirectory inside Flanker. The example is called Stable Diffusion, and there's a link here to that. It's a small large language model that has been pre-trained, and you can ask it to show you images of various interesting things, and it will use that pre-trained model. It will evaluate the pre-trained model on the context input that you give it, run that on a GPU, and then show you the resulting image. So kind of a common thing these days, but is easily handled by the cluster in an interactive fashion. And then once you get into this Stable Diffusion, you just run this script. And you can do that yourselves. I've done it myself already. The first time you run that script, it's going to set up the Stable Diffusion environment. That's going to take about 4 or 5 minutes. Thereafter, when you rerun the script in the same session, it'll start up much faster. So I've already done that, and the image I'm going to show you, I've already gone through this. And that's all there is to it. I suggested that we use the NVTop tool to show how the GPU is actually being used. So let's proceed. If you bring up a web page and type greatlakes.arc-ts.umich.edu, greatlakes.arc-ts.umich.edu, you will get to the Open on Demand front page. If you're if you're already almost out of your home directory space, you get this nice little red warning up here now. If you go to where at the top here where it says interactive apps, it will give you a list of all the things all the sessions you can start. So these were on the slide. I'm going to go down here and select basic desktop. These are all the same kinds of desktops. They're all basically VNC desktops. As you go down this list, you have more and more controls to use for more and more different things. If you're doing something fairly simple, the basic desktop is the easiest to use. So that's what we're going to use today. So if you click Basic Desktop, you'll get to a page where on the side here, it's asking you, okay, what resources do you want to use? This is just the stuff that you had in the preamble of your batch script. So I'm going to use the support account for this because I have access to it. But if you click this, it will show you all the accounts you have access to. And you can pick the one you want. The partition that you want to select is SP GPU. So we have 3 GPU partitions. The SP GPU partition has a lot of GPUs in it that are single precision. And they are perfectly fine for doing machine learning applications. So that's what we're using. You can use the standard partition. Those are the standard double precision, but they're a little bit more heavily used and there's not as many of them. And then the GPU MIG 40 is a new partition that has a couple of very highly capable latest model GPUs in them, but they have been statically split up into two shards, and they're available too.
So the difference between, for example, the large memory one and the GPU is that the GPU by nature is a lot more powerful, whereas the large memory can.
Yes. So the large mem is like standard. It's an entirely CPU node. There's no GPUs on it. It just has 1.5 terabytes of memory on each machine. And there's not that many of them. The GPU nodes are like the standard partition nodes, but they also have GPUs plugged into them that you can then use and allocate to your job. Okay, and then I'm going to ask for 4 cores. Even a GPU job needs some amount of CPU cores. I asked for 4 hours. You can ask for 1 because you're not going to need 4 hours. And I asked for 20 gigabytes of memory because that's the maximum you can get for a GPU job, for a job on the training partition. And then the number of GPUs is 1. When you're done with that, you click Launch. I'm not going to do it because I've already done it. But when you click Launch, it will say, I've launched them. And you'll wake up on this page where you will have a basic desktop that will probably say starting up. It'll take less than a minute to start up, often way less. Once it starts up, this blue button will appear that says Launch Basic Desktop. At that point, you can click that and be connected to your desktop. I did this exact same thing earlier this morning, and I can now reconnect to my desktop. So I've already set this up. You'll have a blank desktop, right? When you are in your desktop, the first thing you'll want to do is start up a terminal. See if I can. So if you go under Applications, Terminal Emulator, you'll start up a terminal. And then at this point, you'll want to cd into the directory that's on the slide and type that command run.sh. As I said, I've already done this. I did it here. And what it will do is it will create a whole bunch of stuff and then pop up this window. Might have to do this again. All right, we'll do it again. So I'm going to go over here. And so the directory I'm in here is flanker stable diffusion. And in here, I just bash run.sh. You do the same thing. You'll get this exact same output. But see where it says launching web UI? It will take you about 5 minutes to get to this spot because you haven't yet built it. But once it creates the web UI, then you should see this. You'll see this exact same thing. It'll just take a little while. And so this is our large language model. You can pick various different sampling methods and various and how many steps you want it to go through when it's creating your image. Up here, in the prompt, you type what you want to see. So how about brain imaging scanner with attendant computer hardware. And then type, and I'm going to move my window because this over here, this is NVTop. So in that directory that has the run.sh script in it, there's also a command file called NVTop, and you can run that. And when you run that and you can copy it around to like different places, like into your bin directory or something. When you run it, it will show you what the state of the GPU is on that you have. So I have a GPU right here. It's doing a whole lot of nothing right now. But this will show me what happens when I run this request.
It looks like attendant is typo. Typo in the text prompt.
Oh, did I type something wrong? Attendant, yeah, let's try. But see, so it drew got a nice image of a brain there, but I'm not sure what the other stuff is. Attendant, let's see what that does. So you see the spike in the GPU that it used while it was generating the image. And you can, for example, change the sampling method. There are some that are more expensive. You can increase the number of steps, and when you do that, you'll see that that bar moves a little bit more slowly, and you see that the GPU is a little more heavily in use. And so you can run this several times on the same prompt, and it'll give you a different image every time. There's a small amount of randomness in it. But this is just a demo to show how easy it is to use a GPU in a machine learning application. So you see here we've got some amount of use of the GPU. And so you can play around with this. You can ask it whatever images to draw. You can change. There's actually the link on the web page points to the Git repository for this this tool. In the documentation, you can substitute different pre-trained models. There are better pre-trained models than this one now, and you can get better resolution at least out of things. So that brings me to the end of what I was going to talk about. The rest of the slides, which I'll just bring back up here, and it's the same kind of deal. You will have the desktop session until the amount of time that you've asked for is over, and then it will be killed. A nice thing is, you saw what I did here. I was able to reconnect to a session that I had started this morning when I was over in my office. So once you create the session, it will stay around until, and you can reconnect to it. You don't have to stay connected to it, and whatever it's doing, it will keep on doing. In fact, I started up run.sh, and then I just disconnected, closed my lid, and came over here. And while I was walking over here, it was doing the initial computation. The rest of this just talks about the support that we have. You are all bona fide users of Great Lakes, which means that you have access to any of these training courses, so full training courses that we offer 3 times a year. There's registration is there. We have office hours, 2 sets of office hours every week coder spaces. There's going to be a coder spaces at 1:30 that I will be in, that anyone at the U can come and ask, questions, hang out, get help with things. There's also LSA-specific research support office hours 3 times a week at that link that will do the same thing for LSA users. And John and Leslie typically hang out in there. Documentation is here that will give you information about the cluster. There's a great user's guide that you can follow that sort of does what I did, but in a little more detail in how to get on the cluster, how to copy data, how to set up jobs, etc. A 2-page cheat sheet that gives you the most critical Linux commands that you need to know. And there's a copy of the sensitive data guide as well. For any problems that you have using the cluster, there's some examples. Send an email to arcts-support@umich. That'll get triaged into a ticket that will be given to our group if it's for us, and one of us will be glad to help you with this. If you have questions with security or any things that you think might be a security issue that you observe, contact your unit IT support staff for that. Anything that you see that might be an issue with ARC, send in a ticket on Great Lakes. And that's it. That's my address, but again, ArcTS-support. Thank you for your attention. Go forth and compute. It'll be.
Thank you.
Thank you.